Hello everyone, today I'm going to be talking about tree adjoining grammars. It turns out that context-free grammars are not suitable for generating all languages. There are some languages that you can't generate with a context-free grammar. These are known as non-context-free languages. Natural languages are non-context-free. This wasn't always known though. There was a paper by Stuart Schreiber called Evidence Against the Context-Freeness of Natural Language, where he demonstrated that particular construction in Swiss German was isomorphic to something that was a known non-context-free language, ergo proving that, at least for the case of this Swiss German construction, that natural language wasn't always context-free. So this particular phenomenon that he discovered was called cross-serial dependence. Since that paper, there have been attempts at modeling natural language not with a context-free grammar, but with a context-sensitive grammar. And the tree adjoining grammar is an example of a context-sensitive grammar. So how are tree adjoining grammars formally defined? A tree adjoining grammar is defined by a five-tuple consisting of non-terminals, terminals, initial trees, auxiliary trees, and a start symbol. Now, some of these things are familiar from context-free grammars. For example, terminals, non-terminals, and a start symbol, but initial trees and auxiliary trees are new and specific to the tree adjoining grammar. So, what is an initial tree? An initial tree is a tree of which the interior nodes are all labeled with non-terminal symbols, and the nodes of the frontier are either labeled with terminal symbols or with non-terminal symbols, which are marked with a substitution marker. An auxiliary tree is defined as an initial tree, except that exactly one of its frontier nodes must be marked as a footnode. The footnode must be labeled with a non-terminal symbol, which is the same as the label of the root node. Now, these definitions can kind of seem confusing, but we'll see an example on the subsequent slides, which it's not very complicated. On this slide, we have some initial trees, alpha 1, alpha 2, and alpha 3. We can see that with these examples that the definition holds true that 1, the interior nodes are all labeled with non-terminal symbols, and that 2, the frontier nodes are either labeled with a terminal symbol or with a non-terminal symbol that is marked with a substitution marker. Notice the substitution marker labeled on alpha 1 on the MP node. On the slide we also have some auxiliary trees, beta 1, beta 2, beta 3, and beta 4. We can see that these trees satisfy the constraints of the auxiliary tree definition, that one of the frontier nodes must be marked as a footnode and labeled with a non-terminal that is the same as the root node. Notice that we can look at beta 1 and see that VP is marked as a footnode and that VP is also the root of the tree. So far we have talked about the productions that make up tree adjoining grammars, but not how to apply them. Applying successive substitutions and adjunctions on initial and auxiliary trees, we develop derived trees. Substitution and adjunction are the fundamental operations of the tree adjoining grammar. We will see some examples on subsequent slides, but first we will formally define the operations. Substituting a tree alpha and a tree alpha prime simply replaces a substitution node in alpha prime with alpha, but only if the non-terminal symbol of the substitution node is the same as the root of alpha. Adjoining auxiliary tree beta at some node n of a derived tree gamma proceeds as follows. Firstly, the non-terminal symbol of the root node of beta should be the same as the non-terminal symbol associated with n. The subtree T of gamma rooted by n is removed from gamma and beta is substituted for it instead, where t is substituted in the footnode of beta. Here we can see a simple example of substitution. In figure 1, we have initial trees alpha 2 and alpha 3. In figure 2, we have the result of the substitution where the D node in alpha 3 is substituted by alpha 2. On this slide, we see an example of adjunction. We have beta 3, which is an auxiliary tree, and the tree T from the previous slide. We can see that T contains a node N that is the root node of beta 3. We can insert beta 3 at this location and move N subtree to the footnode of beta 3, resulting in the derived tree T1. On this slide, I demonstrate how the tree adjoining grammar can be used to solve a problem that we have seen in class multiple times. Our grammar is made up of the set of non-terminals S, the set of terminals A and B. Our set of elementary trees are provided on the slide, and our goal is to generate some number of A's followed by the same number of B's. This problem demonstrates the power of adjunction and can be solved by repeated adjunction. Here I have some references that I found helpful while I was creating this PowerPoint.